In this video, we are going to learn about thermochemistry, subtopic calorimeter, part 1. Let's start with some introduction to this subtopic. Calorimetry is a method used to measure heat flows in a reaction or a process, while calorimeter is a device used to measure the heat released or heat absorbed by a physical or chemical processes. Shown here are the two types of calorimeters that you will learn about. Stay tuned! Since calorimetry is about the measurement of heat, each substance involved will have a certain amount of heat capacity. Now, what is heat capacity? Heat capacity, or the symbol capital C, is the amount of heat, or Q, required to raise temperature of a given quantity of a substance by 1 Kelvin or 1 degree Celsius. If we put the definition into a formula, the formula would be capital C equals Q over delta T, where Q is the heat released by a substance and delta T is the change in temperature. The unit for heat capacity is joule per Kelvin or joule per degree Celsius. We can rearrange this formula to get the formula of heat released or absorbed in the reaction. The formula would be Q equals capital C delta T. This formula will be used a lot in calculating values of enthalpy of a reaction later in this subtopic. If a mass of a substance is given, it will have a specific heat capacity. Specific heat capacity, or the symbol small c, is the amount of heat, or Q, required to raise temperature of 1 gram of a substance by 1 Kelvin or 1 degree Celsius. The formula of specific heat capacity is small c equals Q over m delta T, where Q is the heat released by a substance, m is the mass of a substance, and delta T is the change in temperature. The unit for specific heat capacity is joule per gram per Kelvin or joule per gram per degree Celsius. If we rearrange the formula of specific heat capacity, we can get the formula of heat absorbed or heat released in a process or a reaction. The formula would be Q equals m small c delta T. Please bear in mind that heat capacity and specific heat capacity are two different terms and are to be used in different conditions. Please make sure that you know the difference between them. Other important things that you have to know is the formula of change in temperature, or we call it as delta T. And the formula is final temperature minus initial temperature. For your information, a calorimeter is a closed system, so the heat released or absorbed from a reaction will only circulate inside the calorimeter. Hence, Q released in a calorimeter plus Q absorbed in a calorimeter will equal to the Q system. And since calorimeter is a closed system, so there will be no heat transferred in and out of the system. So Q system is equal to 0. Hence, we can get the Q released plus Q absorbed equals to 0. And lastly, we can rearrange the formula to get Q released equals negative Q absorbed. You will use this formula a lot later when calculating enthalpy of a reaction. Now, let's try to answer some questions using all the formula we've encountered in the previous slides. Given in the question is a process of heating a metal where a 50 grams mass of a metal is heated to 100 degrees Celsius and plunged into 100 grams of water at 24 degrees Celsius. The temperature of the resulting mixture is 28 degrees Celsius. To answer this kind of question, you have to understand the situation given. What happened in the question is a 50 grams metal is heated up to 100 degrees Celsius, and then this metal is plunged into water with initial temperature of 24 degrees Celsius. When the metal is plunged into the water, this causes the temperature of the water to increase to 28 degrees Celsius. Please remember that heat flows from a hot body to a cold body. So in this case, the hot metal will release its heat into water. Question A asked how many joules energy did the water absorb? In order to calculate the energy that the water absorbed, we have to use this formula. Q equals mc delta T. This is the formula that is derived from the formula of specific heat capacity. Since the mass of water is given in the question, you have to use the formula that has mass in it. M is the mass of water, which is given in the question. Small c is the specific heat capacity, which is also given in the question, and delta T is the change in temperature, which you have to calculate. In case you don't know how to calculate delta T, it's final temperature minus initial temperature. And in this case, the final temperature of water is 28 degrees Celsius and the initial temperature of water is 24 degrees Celsius. Hence, delta T will be 4 degrees Celsius. Then, just multiply everything together and you'll get the final answer, which is 1672 joule. Keep in mind that the unit for heat energy is joule. Question B asked you to calculate the heat released by the metal. In this case, we have to use this formula in order to determine the heat released by the metal. Heat released by metal is equal to the negative heat absorbed by water. If you remember, this is the formula that I've shown you in the previous slides. Hence, you will get the value of heat released by metal is equal to negative 1672 joule. The negative value indicates that the process is exothermic. Question C asks you to find the specific heat capacity of the metal or small c. This is the formula of specific heat capacity. Small c equals Q over m delta T, where Q is the heat released by the metal, which is negative 1672 joule, m is the mass of metal, which is 50 grams, and delta T is the change in temperature. In this case, delta T for this metal will be a negative value. This is because the initial temperature of the metal is 100 degrees Celsius, while the final temperature is 28 degrees Celsius. Hence, delta T will be negative 72 degrees Celsius. But worry not, this negative value will be cancelled out by the negative value of the heat. Then, just substitute all the value and the specific heat capacity of the metal will be 0.46 joule per gram per degree Celsius. The last question asks you to find the heat capacity of the metal. Using the formula of heat capacity, which is capital C equals Q over delta T, just substitute the value of heat that you have calculated before divided by the change in temperature. Like that, the heat capacity will be 23 joule per degree Celsius. That's the end of this video. I hope you learned something from it. Thank you. In this video, you will learn about thermochemistry subtopic calorimeter part 2. There are two types of calorimeter that you have to learn. It is bomb calorimeter and also coffee cup calorimeter. Shown here are the examples of the calorimeter. Generally, in a calorimeter, a reaction will occur and the heat released by the reaction will be absorbed by the calorimeter and the water or the solution. This will be explained in more detail later. Calorimeter allows us to calculate the amount of heat released by a reaction. Therefore, we need to know the basic principle in calorimeter. In a calorimeter, heat released by a reaction is equal to the heat absorbed by water and calorimeter. If I put this into a formula, it will be Q reaction equals negative Q water plus Q calorimeter. Remember, Q is the symbol of heat. And the formula for heat absorbed by water is mW small cw delta T, where mW is the mass of water, Cw is the specific heat capacity of water, and delta T is the temperature change. And the formula for heat absorbed by calorimeter is capital C delta T, where capital C is the heat capacity of calorimeter and delta T is the temperature change. Please note that for water, you have to use specific heat capacity, while for calorimeter, you have to use heat capacity. Now, let's go through the calorimeter one by one. The first one is the bomb calorimeter. Bomb calorimeter is used to measure the heat of a combustion reaction only. How does a bomb calorimeter works? Basically, the combustion reaction will occur here at the sample bed, and then the heat released by the combustion reaction will be absorbed by water and also by the calorimeter. Please remember that this whole thing is a system. So, the heat of a system is equal to heat of water plus heat of calorimeter plus heat of reaction. And since this system is a closed system, so no heat enters or leaves the system, causing the value of total heat of the system is equal to 0. Hence, if we rearrange this equation up here, we can get the value of heat released by a reaction equals negative heat absorbed by water plus heat absorbed by calorimeter. Remember that this reaction has to occur at constant volume. Now, let's try to answer this question. The question says, a sample of magnesium metal weighing 0.14 grams is combusted in a bomb calorimeter containing 300 grams of water at an initial temperature of 25 degrees Celsius. The maximum temperature recorded was 26 degrees Celsius. If the heat capacity of the calorimeter is 1769 joule per degree Celsius and the specific heat capacity of water is 4.18 joule per gram per degree Celsius, calculate the enthalpy of combustion of magnesium and write the thermochemical equation for the combustion of magnesium. To answer this question, you have to understand what is going on in the question. Basically, there is this magnesium metal here that will be combusted, and the heat released by the combustion will be absorbed by the water and also calorimeter. Next, you have to extract out the information that is given in the question, which are mass of magnesium metal is 0.14 grams, mass of water is 300 grams, delta T, which is the change in temperature, is 1 degree Celsius, heat capacity of calorimeter is 1796 joule per degree Celsius, and specific heat capacity of water is 4.18 joule per gram per degree Celsius. To answer question A, you have to know what is enthalpy of combustion. If you remember from subtopic 2.1, enthalpy of combustion is the heat released when 1 mole of compound is combusted completely in oxygen. Basically, in this question, we have to calculate the amount of heat that is released when 1 mole of magnesium has been combusted. The first step is you have to calculate the amount of heat released by the combustion of magnesium in the calorimeter. If you remember, the basic principle of a calorimeter is that heat released by a reaction, in this case combustion of magnesium, is equal to the heat absorbed by water plus heat absorbed by calorimeter. Given this is the formula from before. Hence, using all the values that you have from the question, you just have to substitute the value inside the formula to get the value of heat released by the combustion of magnesium. Negative 3023 joule. However, we haven't answered the question yet. The question asks you to find the enthalpy of combustion of magnesium. That means we need to calculate the value of heat for combustion of 1 mole of magnesium. How can we do that? First, you have to calculate the value of number of mole of magnesium using the formula mass over molar mass, and you should get 0.005833 moles of magnesium. This means that the combustion of 0.005833 mole of magnesium releases 3023 joule of heat. But what about the combustion of 1 mole of magnesium? How much heat energy will it release? You just do cross multiplication to get the value of heat release for 1 mole of magnesium combusted. And that is the value of the enthalpy of combustion. Remember, the unit for enthalpy of combustion is in kilojoule per mole. Hence, the enthalpy of combustion of magnesium is negative 518.26 kilojoule per mole. Do not forget to include the negative sign since heat is released in combustion reaction. question B asks you to write the thermochemical equation for the combustion of magnesium. Remember, thermochemical equation is an equation with the value of enthalpy at the end of the equation. For this reaction, just write down magnesium plus half of oxygen to produce magnesium oxide, and the delta H is negative 518.26 kilojoule per mole. Please make sure that your equation is balanced. Here is something that you have to keep in mind. In some cases, water is considered as part of the calorimeter. Hence, the heat released by the reaction is only absorbed by the calorimeter. This is the formula used instead of this. Now, how do you know when will water be considered as part of the calorimeter? It is when there is no mass of water mentioned in the question. If this is the case, then you only have to use this formula in calculating the heat release of the reaction. Let's see an example for this kind of question. This question says, the combustion of 1.010 grams sucrose in a bomb calorimeter causes the temperature to rise from 24.92 degrees Celsius to 28.33 degrees Celsius. The heat capacity of the calorimeter is 4.90 kilojoule per degree Celsius. What is the heat of combustion of sucrose expressed in kilojoule per mole? If you notice here, there is no mass of water mentioned. That means water is considered as part of the calorimeter. These are some information that can be extracted out from the question. Mass of sucrose is 1.010 grams, delta T, which is the temperature change, is 4.1 degrees Celsius, and heat capacity of calorimeter is 4.90 kilojoule per degree Celsius. This information will be used in your calculation later. Therefore, to answer this question, the heat released by the combustion of sucrose will be absorbed by the calorimeter, and this is the formula. Using all the information that you have extracted out from the question, just substitute the value into the formula. Heat capacity of the calorimeter is 4.9 kilojoule per degree Celsius, and the temperature change is 3.41 degrees Celsius. Hence, the heat released by the combustion of sucrose is negative 16.71 kilojoule. Please note that the unit here will be kilojoule since the value of heat capacity given to you is in the unit kilojoule. In order to determine the enthalpy of combustion of sucrose, you have to know what is the amount of heat released for 1 mole of combustion of it. In order to determine that, you have to calculate the number of mole of sucrose first using the formula mass over molar mass. And you should get 0.002953 mole of sucrose in the reaction. This means that combustion of 0.002953 mole of sucrose releases 16.71 kilojoule heat. But how about the combustion of 1 mole of sucrose? How much heat will it release? You just do cross multiplication to solve this equation. And you should get the amount of heat released for combustion of 1 mole of sucrose is 5658.31 kilojoule per mole. Hence, the enthalpy of combustion of sucrose is negative 5658.31 kilojoule per mole. Please remember to include the negative sign since in combustion reaction the heat is released. The next calorimeter that you have to learn is called coffee cup calorimeter. Coffee cup calorimeter is used to measure the heat of any reaction other than combustion reaction like neutralization and heat of solution. But mainly, we are going to learn about the neutralization reaction. Now, how does coffee cup calorimeter works? So the reaction between acid and base will occur inside the calorimeter, and the heat released from the reaction will be absorbed by the solution formed and by the calorimeter. The basic principle of a coffee cup calorimeter is quite different compared to the bomb calorimeter. This is because the total heat of the system is equal to the heat of solution plus heat of calorimeter and heat of reaction. There is no heat of water because the heat released from the neutralization reaction will be absorbed by the solution that is produced from the reaction between acid and base. Hence, if we rearrange the equation, we can get that the heat released by the reaction equals to the heat absorbed by the solution plus the heat absorbed by the calorimeter. And these are the formula for the heat absorbed by the solution. M is the mass of the solution, Cs is the specific heat capacity of the solution, capital C cal is heat capacity of calorimeter, and delta T is the temperature change. Please remember this formula as you will use this a lot in the calculation of enthalpy of neutralization. Now, let's try to answer this question. The question says that 25 cm³ of HCl and 25 cm³ of sodium hydroxide aqueous solution, both at initial temperature of 30 degrees Celsius, are mixed in a calorimeter. The maximum temperature of the solution is 36 degrees Celsius. The heat capacity of the calorimeter is 25.12 joule per degree Celsius. And the question asks you to calculate the enthalpy of neutralization for the reaction. First, you have to know what is going on in the question. So the reaction occurs between HCl and NaOH, and that is called as neutralization reaction. If you remember, the reaction between HCl and NaOH will produce NaCl plus water. So, the heat released from this reaction will be absorbed by the solution produced from the reaction. And that is the value of enthalpy of neutralization that you have to calculate, the heat released from the reaction. And here is some information that you can get from the question. The volume of hydrochloric acid and sodium hydroxide is 25 cm³. The molarity of hydrochloric acid and sodium hydroxide is 1 molar. The delta T is 6 degrees Celsius, and the heat capacity of the calorimeter is 25.12 joule per degree Celsius. First, you have to calculate the value of heat released from the neutralization reaction. In this reaction, the heat released by the neutralization reaction equals to heat absorbed by solution plus heat absorbed by calorimeter. And this is the formula. If you notice here, in the formula, there is the term mass of solution. However, if you refer to the question, there is no info given about the mass of solution at all. Instead, what's given to you is the volume of the solution. So, what you have to do is you have to convert the volume of the solution to the mass of the solution. In order to convert volume of solution into mass of solution, you have to assume the densities and specific heat capacities of the solution are the same as for water. This is because we are going to use the density of water to convert the volume of solution into mass of solution. Now, let's calculate the mass of both HCl and NaOH. This is the volume of HCl. In order to find the mass of HCl, you just have to multiply that with the density of water, which is 1 gram per centimeter cube. And you should get the mass of HCl is 25 grams. Same goes for sodium hydroxide. The volume is 25 cm³. Multiply that with the density of water and you should get the mass of NaOH is 25 grams. Hence, the mass of the mixed solution is 50 grams. You have to take into account mass of both solutions since this reaction involves two reactants. Once you have calculated the mass of the solution, you can now substitute all the values into this formula, like this. M is the mass of solution, Cs is the specific heat capacity of the solution, C cal is the heat capacity of the calorimeter, and delta T is the heat change that have been calculated before. Remember, we assume that the solution has the same specific heat capacity as water. That's why we are using 4.18 joule per gram per degree Celsius. Then just multiply everything together, so you should get the heat release in this reaction is negative 1404.9 joule. Just a little reminder, the definition of enthalpy of neutralization is the heat release when 1 mole of water is formed from the reaction between acid and base. In this case, 1 mole of water is formed when 1 mole of HCl reacts with sodium hydroxide. That means you have to calculate the number of mole of both HCl and sodium hydroxide in order to know how much heat is released in the formation of 1 mole of water. In this case, the formula for number of mole is molarity times volume since they are both aqueous solution. So you calculate the number of mole of both HCl and NaOH, and you should get the same number of mole, which is 0.025 mole. The reason why we calculate the number of mole of both reactants is because we want to decide which number of mole to use. The number of mole of the limiting reactant is the one that determines the amount of heat released for formation of 1 mole of water. However, in this case, both HCl and NaOH are in stoichiometric proportions. Neither is in excess, neither is the limiting reactant. So we can just use both number of mole. When the number of mole of both reactants is 0.025 mole, that means the number of mole of water produced is also 0.025 mole. Hence, we can conclude that formation of 0.025 mole water releases 1404.9 joule heat. But what about the formation of 1 mole of water? How much heat will it release? As usual, just do cross multiplication and you should get the value of heat release for 1 mole of water is 56196 joule per mole heat. However, the question asks you to find enthalpy of neutralization in the unit kilojoule per mole. So just divide this value with 1000 and you should get 56.2 kilojoule per mole heat. Hence, the enthalpy of neutralization is negative 56.2 kilojoule per mole. Please keep in mind that in some cases for coffee cup calorimeter, the heat lost to the calorimeter is ignored. That means the heat released by the neutralization reaction is only absorbed by the solution. This is the formula. If the heat capacity of the calorimeter is not mentioned in the question, that means the heat lost to the calorimeter is ignored. This is an example for this type of question. This question says, two solutions, 100 ml of 1 molar hydrochloric acid is mixed with 100 ml of 1 molar sodium hydroxide. Initially, both are at 21.1 degrees Celsius. They are added to a styrofoam cup or coffee cup calorimeter and allowed to react. The temperature rises to 27.8 degrees Celsius. Determine the heat of neutralization expressed per mole of water formed. If you notice in this question, the heat capacity of the calorimeter is not given. That means the heat lost to the calorimeter is ignored. Hence, to answer this question, first find out the mass of both solutions involved in the reaction using this method that I've shown you before. So you can get the mass of mixed solution is 200 grams. Then, the heat released by the reaction is only absorbed by the solution since we are ignoring the heat absorbed by the calorimeter. This is the formula. Then, just substitute all the values that you know into this formula like this, where Ms is the mass of solution, Cs is the specific heat capacity of solution, and delta T is the temperature change. And you will get the value of heat release is negative 5601.2 joule. Then calculate the number of mole of both reactants, and as you can see, the number of mole of both hydrochloric acid and sodium hydroxide is the same. So, both HCl and NaOH are in stoichiometric proportions, neither is in excess. That means the amount of water produced from this reaction is also 0.100 mole of water. Hence, we can conclude that formation of 0.100 mole water releases 5601.2 joule heat. And what about the formation of 1 mole of water? Just do cross multiplication and you should get the value of heat release for formation of 1 mole of water is 56012 joule per mole. However, remember, the unit for enthalpy of neutralization will always be in kilojoule per mole. So you just divide the value by 1000 and you should get 56 kilojoule per mole heat. Hence, the enthalpy of neutralization is 56 kilojoule per mole. That's the end of this video. I hope you learned something from it. Thank you.